What's up, Algebra Bros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, welcome. Today we get to talk about some of my favorite material, eigenvectors and eigenvalues. Love this stuff so much. Let's go ahead and talk a bit about what it is to be an eigenvector, what it is to be an eigenvalue. Okay, we say an eigenvector of an n by n matrix A is a non-zero vector x, so a non-zero vector x, such that A times x is equal to lambda times x for some scalar lambda. So here x is some vector, right? A is a matrix, x is a vector, lambda is a scalar. We say a scalar lambda is called an eigenvalue of A if there is a non-trivial solution, vector x, of ax equals lambda x. And such a vector x, is called an eigenvector corresponding to eigenvalue lambda. So these things really go hand in hand. I like to think of them sort of as a nice sort of pair. We have an eigenvector x, we have an eigenvalue lambda, and they really they like to be sort of grouped together, right? And an eigenvector is lonely without its eigenvalue, and vice versa. Okay, so really what we're talking about is if I take this matrix A and multiply it to this vector x, some non-trivial vector, then I'm hoping to get out some scaled version of that vector x. And then that scalar affecting that vector x is the eigenvalue, and that corresponding vector x is the eigenvector. And let's go ahead and talk about how we can sort of explore these a bit further. So how can we show that a given vector, let's call it V, is an eigenvector of a given matrix A? Well, okay, so let's say given vector V and matrix A, we want to multiply A times V and check to see if the product is a scaled version of vector V. So I'm thinking A times V would be equal to some number lambda times V. And if this is true, then that vector V is an eigenvector. So if I'm given the vector V and the matrix A, it's actually not so bad to check. I would just multiply A times V, and then I want to know, well, what do I get out? Am I getting something that looks similar to vector V back out? Is it just a scaled version of that vector V back out? If that's the case, then yeah, I got an eigenvector. And I'd be able to find what the corresponding eigenvalue is. Well, what if I was given a constant lambda? How could I tell or find out if that constant lambda is a proposed eigenvalue of matrix A? So this is going to be a bit more involved than the other case. So we'll say given constant lambda and matrix A, we check that A times, we'll use V here, that A times V is equal to lambda V for some non-trivial vector V. So for non-trivial vector V. And how could I go ahead and work with this any differently? Well, I can subtract everything over to the left. Let's do a bit of work here. A times V minus lambda times V is equal to 0. Now, this isn't the constant 0 that I have on the right-hand side. This is the vector 0. And if I want to work with this further, on the left-hand side, I can factor V out, and I should factor it out to the right. So I'll say, well, okay, let's factor V out. And then what am I left with? I'm left with A minus lambda. However, I have to fix this a bit. Because what is A? A is a matrix. What is lambda? Lambda is a number. And it doesn't make sense to subtract a number away from a matrix. That operation isn't defined. But if I want to do something like this, if I really want matrix minus a number, I have to do matrix minus, then I need the number times the identity matrix of the correct size. I'll call that IN. And this is something that I can do, because now it's really a matrix minus another matrix, but I've just scaled the identity matrix. So I really need this in as some multiplicative identity to allow for that operation to exist. Because I wouldn't be able to, take a matrix and then subtract a number, right? Just so you see how kind of crazy that would look. Let's say I have a matrix like, 1, 2, 3, 4, and then minus the number 7. It doesn't make sense, right? I won't be able to subtract a number from a matrix. However, I could do something like minus, and then I could do 7 times the 2 by 2 identity. This would make sense, right? So I could do something like this. I wouldn't be able to do matrix minus number. That's, no. But I can do matrix minus some scalar times the identity. So now what this is really describing is describing an augmented system. And think about this, if we knew what these pieces were, we would just solve for what this is as a coefficient matrix. So I would have some coefficient matrix. I know it looks complicated, but think of this just as some coefficient matrix. You call it B if you'd like something else. And then augmented with the 0 vector. And I want to solve this for a non-trivial solution. And I'm hoping that this has some free variable. So we hope there is a free variable, at least one free variable, right? And if that is the case, then we'd be able to say, so we'd say if yes, if true, then lambda is an eigenvalue and the non-trivial vector v that acts as a solution to this, if this is consistent and with some free variable, then the non-trivial solution vector v is an eigenvector. We'd say the corresponding eigenvector. That would be the corresponding eigenvector then. Okay, well, enough talking about it. Let's see this stuff in action. Is lambda equals 2 an eigenvalue of this matrix? Why or why not? I want to answer the question. So I'm given an alleged eigenvalue. I don't know if it is or isn't. I'm trying to answer that question, and a matrix. So this is the process that I'm going to follow, right? I'm given some constant, hoping it's an eigenvalue. I'm very optimistic. But if it isn't, then we'll find that out too. And a matrix A. How would I check? Well, really what I want to do is I want to build A minus that constant times the identity of appropriate size and augment it with the 0 vector and try to solve for a non-trivial solution. So in this case, I want to build, we'll call this matrix A. I want A minus lambda times I, so A minus 2 times I, and that would be the 2 by 2 identity since I have a 2 by 2 matrix to start. Well, how's it going to look? Well, let me rewrite my matrix. And then minus 2 times my 2 by 2 identity has rows 1, 0, 0, 1. And go ahead and bring that eigenvalue in. If you want to bring the subtraction in with it, you can. But let me go ahead and rewrite that, and then minus, so 2 times the identity is 2, 0, 0, 2. And then I want to subtract. And really what we're going to see as the effect here is on the main diagonal, we're going to be subtracting that eigenvalue, alleged. We're going to see if it is. And off the main diagonal, nothing's going to happen because we're subtracting 0 there. So in this upper left corner, 3 minus 2 gives me 1. For the rest of that row, 2 minus 0 keeps my 2 there. And then here, bottom left, 3 minus 0 keeps my 3. And then here, bottom right, 8 minus 2 gives me 6. So I'm really subtracting on this main diagonal. And everything else is preserved. So this is how that matrix A minus lambda I looks. And what did we say we wanted to do? We said we want to take this as a coefficient matrix and augment it with the 0 vector. So augment it with 0, 0, and then solve this. So what I could do is I could go ahead and scale this second row. So I'll do, okay, 1/3 row 2 And that's going to scale so that it's now identical to the first row, because if I divide by 3, it's going to give me 1, 2 augmented with 0. And then I can actually eliminate that second row. So I can do row 2 minus row 1 in row 2's position. So I'm going to have 1, 2 augmented with 0, and then 1 minus 1, 2 minus 2, 0 minus 0 gives me 0 for all of those entries. And this is what I'm left with. So I could answer the question now, but let's get the satisfaction of actually building the eigenvector. So if I want to build the eigenvector, just write this out as an equation. So what is this saying? This is saying, 1v1 plus 2v2 equals 0. And then if I want to solve here, for example, I could solve for v1. So we'll say, well, v1 is equal to negative 2 times v2. And think of these just as the entries to a vector. So my vector v has entries v1 and v2. And then I want to find a numerical vector. And you could do this with the free variable if you'd like, though you don't necessarily have to. So there's a couple possibilities. Let me show what I would do. What I would do is I would actually just pick a value for one of these. And it looks like v2 is my free variable. So I would probably do something like this. I would say let v2 equal negative 1. So then v1 is negative 2 times negative 1, which is 2, which tells me that my vector, my eigenvector, has a first entry v1, which is 2, and a second entry v2, which is negative 1. Now this isn't the only possible eigenvector you could build. Any scaled multiple of this besides multiplying by 0, don't multiply by 0. It has to be a non-trivial vector, but any scaled version of this would be fine. So you could multiply this all by a negative 1, you could multiply it all by 7, and that would still be a suitable eigenvector. Like I said though, you can also build this with the free variable. So if I go here to this description, let's see if we can go another route with this. I could make substitutions. I could say, well, let me replace v1 with negative 2v2, since that's what it's equal to. And then I'm going to leave v2 as itself. And then I can actually scale v2 out. And what that leaves behind is this numerical vector, negative 2, 1. And notice this is just a scaled version of this vector. This is the same vector times a negative 1. Negative 2, 1 could also be an eigenvector. It depends on where you want that minus sign. These are both suitable candidates for the eigenvector. So as you see, there's a little bit of choice that we get, a bit of option paralysis, if you will. Any scaled version, because you could say, well, let v2 be any non-zero constant, and it's going to give me a non-trivial vector here. You could let v2 be 7 or 3 or 500, but, I'm born to be mild. I don't want to go too crazy with this stuff. So I think either one of these two are the nicest looking eigenvectors, and you'll notice that they're not crazy dissimilar. They're just scaled versions of each other as non-trivial vectors. But that's the idea. That's the idea. So don't go crazy building your eigenvectors. You can put a little bit of personal touch on them, but try to make them look as nice as possible, because you're going to have to work with them later on. So the nicer they look, the better. Well, now we can answer the question. Since we were successful, we can say yes. Lambda equals 2 is an eigenvalue with associated eigenvector, and I like this one here. Call it x if you want. I'm calling it v, whatever you want to name your vector. My eigenvector 2, negative 1. What about this one? So this says, is this vector 1, 3 an eigenvector of this matrix? And if so, find the eigenvalue. So we talked about this at the very beginning. This is a bit different. Here we're given a vector and a matrix. We want to know, is that vector an eigenvector? In this case, I just have to multiply a times v and check to see if that gives me a scaled version of vector v back out. So let's say, well, this is matrix A, this is vector v. Let's check a times v. Right? What does that give us? What's the worst that could happen? So I'm going to rewrite matrix A that had row 1, negative 1, 6, negative 4. I'm going to multiply this to that vector v with entries 1, 3. And let's multiply with our row vector rule. So what does this give me? I get 1 times 1, which gives me 1, plus -1 times 3, which is -3. That's my first entry. For my second entry, multiply the first and the second entries respectively and add the products. So 6 times 1 gives me 6, plus -4 times 3 gives me -12. And let's go ahead and do the arithmetic. So 1 minus 3 gives me -2. 6 take away 12 gives me -6. And hey, is this a scaled version of vector 1, 3? Yeah, it looks like it. What can I factor out of this? I can factor a -2 out. And when I factor that -2 out, it leaves behind a 1 and a 3. So this is, if I want to, really sort of drive the idea home, this is some constant lambda times vector v. It's that same vector 1, 3, just times a scalar -2. So yes, right? So we'd be able to say yes, this vector v, 1, 3, is an eigenvector. This is an eigenvector, is how we call these, with associated, what's the eigenvalue then? The eigenvalue, I'm sort of staring at it right here, that's lambda equals -2. So this is an eigenvector, and by discovering that it's an eigenvector, I also get to see that the eigenvalue is -2. Very fascinating, very cool stuff. Very, very, very cool stuff. See another similar example. Given a vector, is this vector an eigenvector of this matrix? If so, hey, let me know what the eigenvalue is. Let's check. A times v. We got a 3 by 3 matrix. We have a first row -4, 3, 3. Second row 2, -3, -2. Third row -1, 0, -2. And then times vector v. Vector v has entries 3, -2, 1. And I want to multiply and see what this gives me. So multiply first entries, second entries, third entries, and add the products, and do that moving row by row into the vector. So first row, -4 times 3 gives me -12, plus 3 times -2 gives me -6, plus 3 times 1 gives me 3. That's my first entry. Go to the second entry, second row, 2 times 3 gives me 6. Plus -3 times -2, second entries, -3 times -2 gives me +6, plus -2 times 1, these are the last entries, -2 times 1 gives me -2. Now move down to this third row, we're still doing it, still in it to win it, -1 times 3 gives me -3, plus 0 times -2 gives me 0, plus -2 times 1 gives me -2. Now go ahead and finish the arithmetic here, so this is going to give me -12, and then this is going to give me -3, is going to give me -15. 6 plus 6 is 12, -2 is 10. And then -3, skip over the 0, and -2 gives me -5. Noticing, I want this to hopefully give me a scaled version of this vector if successful. Looks like if I want to get that last entry to be a 1, I should be bringing out a -5. If I bring out that -5, I'm going to be left with +3, a -2 to compensate, and then 1. And yeah, that's the same vector, 3, -2, 1, 3, -2, 1. So this is just a scaled version, some constant lambda, times that same vector v. So yeah, we got an eigenvector. We definitely got an eigenvector, so let's talk about it. Yes, this vector 3, -2, 1 is, I'm happy to say it, is an eigenvector. We have with associated, what's the eigenvalue? What is it? The eigenvalue is lambda equals -5. So we have an eigenvector, we have the corresponding eigenvalue is -5. All right, let's check this one out. Just trying to build a nice foundation because we're going to have to do stuff with eigenvalues and eigenvectors later on. So for now, we're just getting comfortable with them. Is lambda equals 4 an eigenvalue of this matrix? So this is a bit more work then. So what I want to do, remember, I want matrix A minus lambda times the identity. So I have to take this matrix that I'm starting with. So I'm just rewriting it. And I want to subtract away, this is going to be 4 times the identity. Now think about how that 3 by 3 identity matrix is going to look. And just give me a second before you start correcting me in the comments below. I want 4 times the identity. So there should be a 4 out here, 4 times the identity. But if I multiply that 4 in, 4 times the identity, that's just going to give me 4s on the main diagonal, right? So A minus, this should be A minus 4 times the 3 by 3 identity. A minus, and then my 3 by 3 identity times 4, I just get these 4s on the main diagonal where the 1s were. Everywhere else, it's going to leave those 0s behind. So not so bad, right? And then I can do this subtraction. I'm really just subtracting on the main diagonal. 3 minus 4 gives me -1. And then for the rest, I'm just subtracting 0 for the rest of that row. So those are going to stay the same. 0 minus 0, -1 minus 0. And then the second row, 2 minus 0 keeps my 2. But in the middle, I'm going to see something. 3 minus 4 gives me -1. And then 1 minus 0 keeps my 1. And these first 2 entries are going to stay the same. -3 minus 0, bam. 4 minus 0 stays the same. But right here, that's on the main diagonal. 5 minus 4 gives me 1. So this is what I get for that matrix A minus lambda I when lambda is 4. So what I want to do then is I want to, remember what we do, we augment this with the 0 vector and try to solve. So use this as your coefficient matrix, -1, 0, -1. Augment it with 0. And then the same for the rest, right? Rewriting it as a coefficient matrix, but augmenting with the 0 vector. Now I'm going to go ahead and I'm going to scale this top row. Right, so I'm going to do -row 1. So that's going to be 1, 0, 1, augmented with 0. That's just a personal preference. I'm going to have to do that probably at some point anyways, if I'm following some proper row etiquette. But now I can start, the real stuff. So I have this 1 in the upper left corner. I want to use that to get 0s directly underneath. Let's go ahead and get in there. So in row 2, I'm going to replace with row 2 minus 2 times row 1. That's a 2 there. Let me fix it. You're worth it. You're here watching the video. You deserve a 2 that looks like a 2 and not just like some afterthought. And then here in row 3, we're going to do row 3 plus 3 times row 1. Yeah. Let me rewrite row 1 to start. Row 2, 2 minus 2 times 1 gives me 0 that I wanted. -1 minus 2 times 0 keeps my -1. 1 minus 2 times 1, that's 1 minus 2 gives me -1. And augmented with 0 minus 2 times 0 keeps my 0. Here in row 3, -3 plus 3 times 1 gives me the 0 that I was after. I'm going to have 4 plus 3 times 0 keeps my 4. And 1 plus 3 times 1 gives me a 4. And then 0 plus 3 times 0 gives me 0. So I can see now if I'm scaling rows 2 and 3, we'll do a negative row 2 and a 1/4 row 3, scaling those, that they should look identical now. So I get 1, 0, 1 augmented with 0. But flipping the sign on row 2, I get 0, 1, 1 augmented with 0. And dividing row 3 by 4 gives me 0, 1, 1 augmented with 0. And then since row 2 and 3 are identical, I can eliminate one of those rows. So we'll do row 3 minus row 2. So rewriting rows 1 and 2. And then in row 3, I'm going to get that row of all zeros. And this is actually fully reduced now. And I do have a free variable, so it looks like I am successful in this. Let's see how this is going to look. So if I write out these equations, I get v1 plus v3 equals 0, v2 plus v3 equals 0, v3 being my free variable. If I go ahead and solve these, I'll get v1 equals negative v3, v2 equals negative v3, and I can choose what I want for v3. Now, in this case, it depends on how you go about picking these, how you build these eigenvectors. I think it would look nicest if I were picking my eigenvector, make sure it's non-trivial, I would let v3 be equal to negative 1. Because it's going to flip the sign on these. I think it's going to look a lot nicer. So v is my vector with entries v1, v2, v3. And when I say let v3 be equal to negative 1, I get the vector v equals, so v3 is negative 1, but then v1 is minus 1, which is 1, and v2 is the same. So I get this nice eigenvector. Now, like we were saying before, you could build this with a parametric vector description if you'd like to. That's another way to actually do this. Is I could say, well, v1 is negative v3, v2 is negative v3, and v3 is itself. And if I just bring v3 out, that leaves behind the numerical vector negative 1, 1. And these are really, scaled versions of each other. So if I ditch that mention of the free variable, I have another possible eigenvector. So another possible eigenvector could be negative 1, 1. I really like 1, 1, negative 1. Are they really that different? No. They're both suitable eigenvectors. Now we can answer the question, what do we have? 4, right? 4 was and it is an eigenvalue. So let's just sort of say what we came here to say. Yes, lambda equals 4 is an eigenvalue with eigenvector, and I'm using this one here, so this is my choice. I think it looks nicer. I like the nicer looking eigenvector. 1, 1, negative 1. Yeah, that's mine. That's mine. Should be yours too. If you like this eigenvector better, let me know in the comments below. If you think this one's better, hey, let me know that too. Let me know what you're thinking. You could also add a shout out to other eigenvectors, 2, 2, negative 2, or other eigenvectors, negative 7, positive 7, or other eigenvector, pi, pi, negative pi for constant pi. Don't go crazy though. Please don't. We're just going to plant some ideas that are going to come in later. Find a basis for the eigenspace corresponding to each listed eigenvalue. So here I have a matrix A, and I'm told this is an eigenvalue, lambda equals 7. I want to find a basis for the eigenspace. Is really just going to be a little bit of extra work at the end, but it's not going to be so dissimilar from what we've been doing. Find the eigenvector. Find the eigenvector. So I'm going to take this matrix A, and I want to subtract away 7 times the identity. So I'm not going to write 7 times the identity. I'm just going to multiply 7 into my 2 by 2 identity. So there's A minus 7 times I2. Looks like this. And let's do the subtraction then. Let's do the subtraction. So here I get 1 minus 7 gives me negative 6. Negative 3 minus 0 is negative 3. Negative 4 minus 0 is negative 4. 5 minus 7 is negative 2. And then I want to use this as a coefficient matrix and augment with the 0 vector. I'm doing it. And let me scale these rows. Let me do a negative 1/3 row 1. Let me do a negative 1/2 row 2. These are going to come out looking nice. So here if I divide by 3 and flip the sign, I'm going to get 2, 1 augmented with 0. If I divide by 2 and flip the sign, I get 2, 1 augmented with 0. So this is a good sign. I got a good feeling I got that free variable. Let's eliminate row 2. Let's replace row 2 with row 2 minus row 1. So row 1 stays. Row 2, 2 minus 2, 0. 1 minus 1, 0. 0 minus 0, 0 in the augmented entry as well. Let's build an eigenvector. This row is telling me 2 times v1 plus v2 is equal to 0. And so you can think of this in terms of a free variable. This is not a fully reduced row echelon form, in fact, so you might already be upset with that. This isn't fully reduced. It's not so important when building an eigenvector to necessarily get a fully reduced coefficient matrix. In fact, I don't even need to stick with a normal sort of framework when it comes to solving this, because in any other context, I would be throwing my arms up in the air, yelling and screaming, saying, hey, the free variable is v2, solve the basic variable in terms of the free variable. But to build an eigenvector, we're just looking for a vector that meets our needs. So since v2 is already isolated, meaning it has no coefficient, or rather the coefficient is a positive 1, it's going to be easier, in an algebra sense, to solve for v2. So if I solve for v2, which is my free variable, let me know in the comment section below if this makes you uncomfortable. If I solve for v2, I get negative 2v1 is equal to v2. And this, I can just play with this to build my eigenvector. This is fine. What am I going to do? I'll be honest, I like that first entry to be positive. Why? I don't know. I don't know why I'm like this, but I like to have that first entry as positive. Who's to judge? But so I would go here and I would say, well, I'm going to say let v1 be negative 1. Well, I actually don't want that. If I want it to be positive, then I should pick positive 1. So I'll pick, that's a positive 1. And then that means that v2 is negative 2 times positive 1, which is negative 2. So this is what I would probably do to build a vector. I'll say my vector v has entries v1, v2. And I said let v1 be 1. And then as a result of this, v2 is negative 2. This works. However, if you do let v1 be a negative 1, then you could have another vector, so another possibility. So I'll jot it up here. Another possibility could be if I let v1 be negative 1, then v2 is going to be positive 2. But this isn't dissimilar from what I already have. Put this in the bonus box. This isn't dissimilar from what I already have, right? There's a scaled version of it. But this is, I like this one because I like that first entry to be positive. But so now that I have an eigenvector, I can build that basis. So let's talk about what that really means. A basis for the eigenspace corresponding to the listed eigenvalue. It's just building a set of the corresponding eigenvector or eigenvectors. In this case, I just have one eigenvector. So we'll say a basis, let me do this in a different color, make it look really cool. Let's get the pink. A basis for the eigenspace corresponding to lambda equals 7 is, it's got to be in a set, and it's this vector that I have with entries 1, negative 2. That's all there is to it. Now, building it's not such a big deal. If you know how to find an eigenvector with a corresponding eigenvalue, then you can build a basis for that corresponding eigenspace with, little to no extra work. But this is going to be important for us to talk about in future conversations. Right now, we're kind of getting an introduction to eigenvalues and eigenvectors, eigenstuff. Let's take a look at another example. Let's find a basis for the eigenspace corresponding to each listed eigenvalue. And here I just have one eigenvalue, -5. I want to take a look at a minus -5 times the identity. I like to think about this a bit before I jump into it. So this is really going to look like a plus 5 times the identity. And it's going to be the 3 by 3 identity since I have a 3 by 3 matrix. So let's build this. Let's build it. I'm going to be, so it's minus a negative. So because of that, I get addition. And then 5 times the 3 by 3 identity. I'm going to have 5s on the main diagonal, but otherwise zeros filling out the rest of those rows. And let's see how this looks, because this is going to become my coefficient matrix, of course. And only on the main diagonal do I see the change. -4 plus 5 gives me 1, and then the rest of those entries in that row stay the same. 2, and at the other end 2, but in the middle, -3 plus 5 gives me 2. 3 and 3 to start, and I'm adding 0 to it, so no difference. But then at the end, -2 plus 5 gives me 3. So this is the matrix that I get. And this is going to be my coefficient matrix. Let's build the eigenvector. So we take it as a coefficient matrix. We augment with the 0 vector. Yes. Nice. And, you know, it looks like scaling the rows here is a good move. You could just go straight into a row replacement. I wouldn't blame you for doing that. But I really want to show that these rows are dependent. 1/2 times row 2 is 1, 1, 1, augmented with 0. 1/3 row 3 is 1, 1, 1, augmented with 0. So this is going to be some quick work here, right? We'll say, let's replace row 2 with row 2 minus row 1, and replace row 3 with row 3 minus row 1. And then row 1, I'm going to rewrite it. But in row 2, 1 minus 1 gives me 0, and again, and 0 minus 0 is 0. And row 3's replacement is the same story. And this is what I'm left with. Okay, so what is this trying to tell me? Well, as a row, it's saying v1 plus v2 plus v3 is equal to 0, or that v1 is equal to minus v2 minus v3, where v2 and v3 are free. Think of those as my free variables. Now, I want to go ahead, and I think it's reasonable to build a parametric vector form of our solution here. So this vector v that I'm trying to build, my eigenvector, has entries v1, v2, and v3. And I can make replacements here. I can say, well, v1 is minus v2 minus v3, where v2 is just v2, and v3 is just v3. But thinking about this, since I have two free variables, this should actually split naturally into two vectors. I get a vector that relies on v2, and a vector that relies on v3. And the vector that relies on v2, it's sort of missing that last entry, but we can think about what it should be. It'd be a -1, +1, 0. And here for v3, missing that middle entry, but it'd be a -1, 0, 1. Now, it's these numerical vectors that I want, and you could in fact scale them through by any non-zero constant. So I'm going to use these vectors, but mark my words, I'm going to flip the signs because I like that first entry to be positive. But you could take these vectors just as they are, and they would be eigenvectors. So this was, what was it? It was -5, I believe, was the eigenvalue. So we'll say a basis corresponding to eigenvalue lambda equals -5 is, and it's a set containing two vectors. Well, let's do this. Let's do something really cool. If you're still watching the video, if you haven't tuned out already, let's do something really cool. There's these two vectors in it. Well, I got to get the comma in there. I got to go back to the blue for the comma. So I can get those vectors really standing out. Now you could just pick, let's do a different color for the entries. We're getting crazy today. You could just write these vectors in. That's fine. That's fine. Me, I'm a little crazy. I like the first entry to be positive, so let's multiply. Let's let v2 and v3 both be -1. So if I let v2 be -1, it gives me the vector 1, -1, 0. And if I let v3 be -1, I get the vector 1, 0, -1. I like this. This looks really nice to me. So this is my basis corresponding to the eigenvalue lambda equals -5. So my basis for my eigenspace right here. And we'll notice that in this previous example, the dimension is 1. I just have one vector in that basis for my eigenspace. But here in this example, I actually have two vectors. This one eigenvalue gave me 2 eigenvectors. So when I said a basis, you could say for the eigenspace corresponding to eigenvalue lambda equals -5 is, I have this set with these 2 vectors in it. Very cool stuff. Let's take a look at this next theorem that we have, and I want to talk a little bit about it, but we're really going to have to merge this conversation into the next lecture. The eigenvalues of a triangular matrix are the entries on its main diagonal. So let's not really, I don't want to try to prove this all out unless you want something like that, but we can explore the idea. Let's just imagine a 3x3 matrix, and it's a triangular matrix. So I'm going to say that the entries on the main diagonal are A, B, and C, for example. And then if it's, doesn't matter if it's upper or lower triangular, let's imagine it's upper triangular. So I'll put the zeros underneath, and then I'll fill in the rest. So A, B, C, D, E, F, something like this. These are just constants, right? So this is my triangular matrix. And if I subtract away, so if I do A minus lambda times the identity, let me rewrite it. Try to give you some justification. Minus, and I don't know what lambda is, but it's some scalar. So lambda times the 3x3 identity would look like this. And if I do this subtraction, this is going to give me, still going to be a triangular matrix, but I have along the main diagonal A minus lambda. And then I still have D and E. And then I'm going to have 0. And then I'm going to have B minus lambda. And then F minus 0 is F. And then 0, 0, and then C minus lambda. So this is my A minus lambda I, where A is a triangular matrix, is how it looks. And in fact, I'm really just subtracting lambda on the entries on the main diagonal. What's going to be crucial to this is noticing that this is still a triangular matrix, so is still a triangular matrix, and the determinant is determinant of A minus lambda I. What's really important to notice here is that we talked about this earlier in the course too. The determinant of a triangular matrix is just going to be the product of the entries on the main diagonal. So the determinant of this is A minus lambda times B minus lambda times C minus lambda. And you're going to wonder why, because we're going to talk about this in the next section. So a bit of a cliffhanger, but we're going to address this. The way that we would find the eigenvalues is by setting the determinant equal to 0. And this is something we haven't talked about yet, but it's the first thing we're going to talk about in the next lecture. It's going to be a big motivation for us for actually finding eigenvalues on our own, not verifying, but finding them, finding what they are. So we'd say here, setting this to 0, we have determinant of A minus lambda I equals 0. The number 0 means 0 equals A minus lambda times B minus lambda times C minus lambda, which means that solving this, we get lambda equals A, lambda equals B, and lambda equals C. And these are, potentially different eigenvalues. You can nickname it lambda sub 1, lambda sub 2, lambda sub 3, for example. But these values A, B, and C were the entries on the main diagonal. So we'll talk about this more in the next lecture. But right now we're saying, and trust me, follow me with this, that the eigenvalues of a triangular matrix are just the listed entries on the main diagonal. Let's use this. Find the eigenvalues for the following matrix. So this, I do have a triangular matrix. It's upper triangular, although I do have a fair amount of zeros up there. But here's my sort of pizza slice of zeros, and I kind of cut off that entry, but remember it's a 3. So so I'd say since this matrix is triangular, the eigenvalues are lambda equals 0, lambda equals 3, and lambda equals -2. Just the entries on the main diagonal, 0, 3, -2. Say it with me, 0, 3, -2. Got the 0, 3, -2. 0, 3, -2. Got the 0, 3, -2. It's like a little song. Kind of got a nice little, it's got a good beat to it. And you know, I like to give these little subscripts. Lambda sub 1 is 0, lambda sub 2 is 3, lambda sub 3 is -2, but these are the eigenvalues. So if I have a triangular matrix and you want me to find the eigenvalues, it's fast work. A nice theorem to end with, and that's going to be it for today. If vectors v1, v2, v3, so on and so forth to v sub r are eigenvectors that correspond to distinct eigenvalues. So these means the eigenvalues are all different numbers, lambda sub 1, lambda sub 2, so on and so forth, lambda sub r, of an n by n matrix A, then the set is linearly independent. So that's going to be important for us to talk about when using these eigenvectors to build bases, etc., etc. That is important. It's going to be important for talking about diagonalization as well. But that is it for today. I'll leave it here on the theorem because that's what we're ending with. I want to say thank you for talking to me about some of my favorite stuff. We're going to talk more about fundamentals and an introduction to eigenvalues and eigenvectors next time. In the meantime, make sure to always keep learning, keep dreaming, and to always follow your heart. You know what? Until next time, I will see you later. Take care of yourselves. Let me know how you're doing in the comment section below. Let me know what you're up to this week. Let me know what you're drinking, if you're drinking coffee or soft drinks. And hey, we'll be back at it soon with more math, more cats. You got it.